So the downtown used to take care of the downtown it's gotten better. When I was beautiful
Okay, I think we can start. It is my pleasure to introduce Professor Nathan Harshman, a good friend and a good collaborator. Nathan made his PhD in Austin, Texas. Austin is the capital of Texas. And for you that know the US and Texas in particular, Austin is a non-common city in the US, so it's quite a lot of weight of science, literature, culture, and so on and so forth. So it's a very nice city. Also, it has a government, it has a capital. So he did a PhD there in Austin on particle physics, so away from quantum information in the moment, but close to symmetries and those stuff. So for all of the people working in photonics, quantum optics, quantum matter, solid state, those are our enemies because they got all the money. But not everywhere. In Spain, yes. In the US, it's more meat. And actually, for the Nobel Prizes, most of the Nobel Prizes comes from solid state, condensed matter, photonics, and from time to time, some spectacular in astrophysics.
Particle. There were decades where particle physics won.
Yeah. So it's something. So he moved in the first postdoc to Rice. Rice is like 6 miles from Houston. Houston is a huge city, and imagine a huge city like Madrid with only one street where you can find bars. So it's extremely boring and hot, and people live in underground.
This is not all true.
You got nice at it.
It's close to true. From a European point of view, but Rice is very nice. Rice has a downtown, it's beautiful, it's bars, restaurants, libraries, so it's super nice also. And then he moved a little bit closer to quantum information, still in particle physics, but closer to quantum information. And then he got a permanent position at Washington, D.C., the capital, in the American University, where he helped recover and grow the physics department. And when he came, there was few people working there. Now there are like 30.
Yeah.
More or less.
Yeah. 5 to 30.
Yeah.
We had 5, now we have 30.
And he does a lot of work, very interesting on quantum info, quantum technologies, few atom systems, in between theoretical physics and mathematics. And very interesting. We met because of symmetries in some moments. We have a couple of papers together. And he's there now for 6 months, or 5 months, or 4 months, or some months. In sabbatical. Okay. So any question you have, you can make during the talk.
Please.
You can make after the talk, or in the next few months you can also.
That's right.
Okay. So
3, 4, or 5. No?
So thank you.
Thank you, Miguel, for the kind introduction.
I apologize that I'm speaking in English. My Spanish would be mixed with Italian and sound like a child, so please let me apologize. And again, this is a talk where I'm not going to assume this is a talk somewhere between physics, math, applied math, a little engineering, a little philosophy, all right? So it's somewhere in the middle of all these things. But the focus, of course, is on symmetry, which can be a powerful tool and a beautiful guide, but it can also, for a physicist, be distracting. And so I'm going to tell a few stories about that. Some of them are directly connected to my research, some of them are more sort of the background for my discipline. But even though I had a good introduction, I'll say just a few words. So again, I am at American University, the Fulbright program, which is a program that brings US scholars abroad, but also brings students from Spain and faculty from Spain to the United States. You might keep your eye open for it. It is a nice program that funds international exchange of scholars and researchers and students. So keep your eye open for that. That's who is funding my visit here partially. American University funding the other half. So, oops. Here we go. So who is American University? Well, okay, yeah, we're in Washington, D.C., so White House, Capitol, we're about 5 kilometers from downtown. We're in sort of a suburb. This is our building. Anyway, if you're ever in Washington, D.C., happy to look up. My university is bachelor's only in physics. So in other words, I usually do teach students in their first 4 years almost exclusively at my home institution. It's a private university, which is common in the US, a little bit of a different thing here in Europe. Anyway, we can go into that. Welcome. So I'm going to talk, even though Miguel Angel did this, let me just say, so I actually did my bachelor degree in both physics and English. So I really do like interdisciplinary work, and it also makes me a little talky. As he said, I did my PhD at the University of Texas at Austin in theoretical particle physics. I got my PhD there in 2001. That's where I started thinking about symmetry. Because people working in the foundations of quantum mechanics, but also particle physics, were the mathematical physicists who developed the tools to make symmetry, to develop the machinery to make symmetry such a powerful tool. Then, as Miguel said, I started a postdoc at Rice University and became assistant professor. That's where I worked in quantum information theory. Quantum information theory in the early 2000s was really, I mean, it still is, but that's when it became hot. If you want to do particle physics, you often have to be part of a huge collaboration. And you have to have lots of social networks, and you have to sort of keep yourself very rushing to the front. Quantum information theory, especially in 2003, had a lot of easy problems that you could solve on your own. So I jumped ship to a new field. And this is just always advice I give to young people. Keep your eyes open for what's new, because sometimes the new things, it's easier to make progress there, right? Anyway, but for the last maybe 15 years, I've been doing what's called few body physics with ultra cold atoms. So in experiments, and this started in the 90s, but now we're very, very good at it, you can take atoms, cool them down to near absolute zero, and trap them in little shapes made out of light. Maybe they are a long cigar-shaped tube, and it's almost like the particles are moving like beads on a wire. Or maybe you can make a pancake trap out of light, and it's like all the atoms are trapped in a plane. Or maybe you can make a lattice out of light, and the particles can hop between the cells in the lattice like some sort of board game with marbles and holes. So we can now tune the shape of the trap, the interactions of the atoms, and all sorts of properties there. And so that's led to a whole new way to probe fundamental physics, fundamentals of quantum mechanics, also to use these quantum systems that we can control to model other systems. And so that's what I've been studying for about the last 10 or 15 years. And the point is in all of these, my main tool was symmetry. So I'm an expert in something called group theory in quantum mechanics. And so symmetry is like a hammer. And I just run around looking for problems that I can hit with my hammer of symmetry. And therefore, turn that into a publication, and the publication into a number, and the number into arrays. Okay, sorry, that was cynical. That was a cynical joke. All right, moving on. Okay, let me just say one more word about my other hat. I am also director of something called the NASA DC Space Grant Consortium. And in 2 weeks in the Department of Aeronautics, School of Aeronautics, I'll be giving a talk more about this other thing I do. So this is a project where NASA realized they were so mission focused on getting satellites or going to the moon that they weren't investing in human resources and education. So they created a program, and I direct that program in the District of Columbia, where Washington, D.C. is, and it's a way to bring NASA money to higher education, to universities, and to try to connect those universities to the NASA centers and NASA missions. So if you're interested, I'll talk about that in a couple weeks at the School of Aeronautics. Okay. Yeah, okay, so now to the real talk. So my favorite kind of mathematical physics can be visualized or can be imagined by thinking about the regular polytopes. So what are the regular polytopes? Okay, so just to say them, right, we have the tetrahedron, cube, octahedron, dodecahedron, icosahedron. Think for a second, what are the properties that make something a regular polytope? So first off, lots of symmetry, right? Can we put it into words? We would say every face is the same, every edge is the same, and every vertex is the same. Or maybe if I was more precise, I would say similar, right? So these shapes, like for example, I have a friend who's a computer scientist who does 3D modeling. And he said, hey, I want to make a sphere with an equal pattern of lights. How many can I put on it, right? I want to have a sphere where the lights are equally spaced. And I said, well, the most you can do is 120, because that's the vertices of an icosahedron. Oh, I think it's 60. I said the wrong number. But anyway, the most you can do is 60. Like, in other words, this is, so, okay. So there's 5 of these. There's 5 of these shapes. There's ones that are a little less symmetric. Maybe their faces and edges are the same, but not their vertices. Those are called Archimedean. There's Keplerian and Catalonian, whatever. But these are the 5 Platonic solids. And it turns out the math you use to classify these shows up all over different branches of math, applied math, and physics. I've just thrown a few of them on here. Everything from like toys like kaleidoscopes, matrix groups, Lie groups, dynamical catastrophes. You may not know most of these words, but these are huge branches of subjects that people study. And it turns out the classification system that was developed toward the end of the 19th century and continues to this day, very, very similar classifications to sort of describe all of these. And this is just sort of one special case of it, right? So there's this, sometimes it's called the Langland problem, right? Or the Langland, this idea that we can connect all of these symmetries and numbers and topology and all that anyway. Okay. But the point is, again, there are 5 Platonic solids. How do we know that? I mean, can someone discover a 5th or 6th? Could someone just go out there and be like, oh, I figured it out, here's another 6. How do we know this? Well, so people have made like dice, like gaming dice, with these shapes for thousands of years, right? For thousands of years. We have prehistoric evidence that these 5 shapes were known. So sometime, by the time we get to the Greeks, right? The Greeks figure out there is actually a way to know things using proofs, right? And so you start out with some axioms, right? And here are the first 4 of Euclid's axioms. The 5th one is a little wonky. There's a long story there about this 5th one being wonky. In fact, right, so a straight line segment can be drawn joining any 2 points. That seems simple enough. The rest of these, all right angles are congruent. That seems simple enough. If 2 lines are drawn which intersect in a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect, blah, 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 right? This is clearly a lot harder than the other ones. Again, there's a whole long story where people spent centuries trying to see if we could prove this one from the other one. In the end, it turns out no. If you make this assumption, you get Euclidean geometry. The geometry we first learn of lines and shapes in planes and spaces, solid and plane geometry. If you break this, you can have other kinds of geometry, like the geometry of special relativity. It turns out, right, there are other geometries than Euclid. You do also need a few rules. And these rules are a little bit different than axioms, although quite honestly, the line between what's an axiom and what's a rule that's a little blurry, right? That's somewhat a matter of taste, and a very hard thing that very talented theoretical mathematicians have thought about for a long time. But the point is Euclid, working based on work from people before him, wrote the 13 books of Euclid, right? And the whole point of those 13 books, the last proposition of the 13th book, is the proof that there are only 5 of these, right? So a couple lessons from this. First off, one reason we remember the Greeks is because they contributed to our understanding of epistemology, our study of knowledge, by saying, this is a way to get to certainty. It's to start with axioms, do deduction to build up to truths, right? And that's a huge contribution to how we begin to order thought in our Western societies, right? So that was a pretty big deal. But also, I mean, this result is important. We never have to look for another one of these. Now, fun fact, there's 5 in 3 dimensions. How many in 4 dimensions? Anybody want to guess? How many in 4 dimensions? In 4-dimensional Euclidean space.
100,000.
Say that. 100,000. Turns out it's 6. In 2 dimensions, there's an infinite number, because that's every single polygon. You can have a 3-sided polygon, or a 4, or a 5, right? A pentagon, or a hexagon. Or you can just go on forever. So there's an infinite number in 2 dimensions. There's 5 in 3 dimensions, 6 in 4, and then for every dimension higher, 3. Right? That's bonkers. Right? That's bonkers. What it actually tells us, in fact, is that 2 and 3, and to some degree 4 dimensions are a little special. Right? If there's any topologists out there, topologists know that there's often weird cases in 2, 3, and 4 dimension, and once you get up to higher, turns out it often gets a little simpler, right? So anyway, so that's one of the lessons of this story. Another one is this idea. Maybe a third idea is these appear, and these other kinds of symmetric figures appear in art all the time, right? These are pretty. These have beauty, right? And the Greeks had this ideal that beauty and truth were sort of the same thing. And this is part of this sort of classical perspective. Right? The Pythagoras is almost a mythical figure. The Pythagoreans were a cult who believed in rational numbers, free love, and no beings. Yeah, those were their 3 big beliefs. Every number was a rational number, a fraction. There should be no monogamy. It should all be free love. And beings are the worst. Beings are the worst. And if you have a bean in our Sicilian compound, we are throwing you into the water and hope you die. Okay, but the point is they have these sort of beliefs like there is geometry in the humming of the strings. There is music in the spacing of the spheres, right? This idea that there's some connection between geometry and beauty, but also the order of the universe. Arithmetic is the discrete at rest. So this is the quadrivium. These are the 4 fundamental topics that a scholar should learn, well, after the trivium. Arithmetic is the discrete at rest. Astronomy is the discrete in motion. Geometry is the continuous at rest. Music is the continuous in motion, right? So this way of sort of mixing together beauty, geometry, and what we think reality is. Maybe another point is, right, I mean, the Platonic solids, right, the Greeks believed there were 4 essential elements, and then, and they were here, earth was represented by the cube, water by the icosahedron, air by the octahedron, and fire by the pointy tetrahedron. Then there was a 5th element that unified them all, and that was the dodecahedron. So they had an ontology, a belief about what the fundamental nature of reality was that was deeply tied to these symmetries that were beautiful. This is a very, very compelling idea, right? Galileo, credited in some sense of being the first real, true physicist, philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. This idea that our universe, the fundamental reality of our universe, is geometric and symmetrical. So, a little after Galileo, we got Kepler. Kepler begins to believe that the universe that there's another way of forming knowledge besides the deduction of the Greeks, that you actually can make measurements. You can make empirical observations. And based on those empirical observations, he is convinced by Copernicus that the solar system is heliocentric and not, right, and not geocentric. But he's still so wrapped up in this view of how math works that he believes that the orbits of the planets can be explained by nesting Platonic solids inside one another. And so he spends a whole book fiddling around trying to figure out what's the right way to nest the Platonic solids so that the 6 spheres that bind them fit perfectly. Mercury, Venus, Earth, right? He spends a whole book doing this. That book's not his best book. Let me tell you, right? That book is him being fooled by symmetry, by the beauty of symmetry, into chasing down a rat hole. Down a hole where there is no light at the end of that tunnel. He ends up, though, writing a better book later, because he does get the data from Tycho Brahe, and he finally figures out they're not spheres, it's ellipses, right? And he comes up with the 3 laws, and it's just it turns out, in some sense, it's a less pretty story on the surface. Now, we can then go to 4-dimensional, or we can go to other dimensions, we can go to more sophisticated mathematical theories, and it's just as beautiful, right? But you have to look at it in a more sophisticated mathematical language. So, I'll say that this approach of mathematizing the universe, right? Eugene Wigner, who was one of the founders of using symmetry in quantum mechanics, so again, that's really what I do. This is one of his most famous quotes. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. Even though this is written in 1960, to me, this is the dream of the Enlightenment, right? That we really will be able to use math to describe everything, right? This beautiful dream, and in fact, the whole world will reduce to that. This essay is called The Unreasonable Effectiveness of Mathematics and the Natural Science, and I would say that symmetry is a big part of this, and this is why I study it. When Wigner is writing, like some of the big successes that were happened was the idea people had figured out that symmetry leads to conservation laws. Emmy Noether was a mathematical physicist working on field theory in the 20th century, right? And she, in this particular formulation, but it generalizes, was able to show that if you have time translation symmetry, meaning that if the laws of physics don't change in time, that implies conservation of energy. Right? So that's sort of a whole new perspective where you have this invariance, this symmetry, and that provides a conservation law. If you have space translation symmetry, if the laws of physics don't depend on where you put the origin of your coordinate system, well then you get conservation of momentum. And finally, right, or maybe not finally, the big 3, there's other ones too, but if you have rotational symmetry, then you get conservation of angular momentum. So there's this fundamental notion between, right, and this is so tempting then, do symmetry, so maybe symmetries don't give us the fundamental constituents of nature, but they give us the laws of nature. Or maybe they even give us the constituents too. So Wigner also worked, and in this time, there's a thing called there's quantum field theory, which is the fundamental theory we think that now describes all the particles and fields in the universe. And I will say, quantum field theory and the standard model, that is the most precise mathematical theory that exists. We can calculate certain properties, the magnetic properties of an electron, for example, to a part per billion and measure it just as accurately. Nothing else comes close to that, right? Like that kind of consilience between theory and experiment, there is no more precise thing than quantum field theory. And the goal of quantum field theory is that there are, well, first off, maybe I would say, how many forces are there? Yeah, we got it, right? There's 4 forces. We believe that there are only 4 fundamental forces in the universe: electromagnetism, weak nuclear, strong nuclear, and gravity. And so in the 20th century, people figured out that whatever gauge symmetry was, that there was some sort of symmetry that has to do with unitary 1-by-1 matrices, that you could somehow understand electromagnetism from this symmetry. And that you could, and Wigner also contributed to this, think about the weak nuclear force. This is the force that is why protons decay into neutrons and, why neutrons decay into protons and electrons, and generally is necessary for understanding nuclear decay in nuclear decay. So it has another kind of symmetry, and then you can understand how the quarks form into nucleons using the strong nuclear field. So anyway, the point of this thing is we have this thing called the standard model, which says if you have quantum field theory obeying this kind of gauge symmetry, that is the most precise theory we have. And it's amazing, and people are still testing it, the Large Hadron Collider at CERN and all these places, and so everybody's looking for like 7th decimal place problems, right, to sort of signal a new era of physics. This is what I studied when I was doing this, is we were looking for part per million discrepancies, hoping that would reveal a new fundamental physics. People don't love the theory for 2 reasons. One, it still has, depending on how you count it, 19 to 27 free parameters. Like, you just have to put these numbers into the theory from somewhere. Like, you have to measure them, right? We don't know where these numbers come from. And right, so there's a whole bunch of people who would love to come up with a theory that explains why these numbers, the mass of the electron, the coupling coefficient for the weak bosons to the Higgs mass, right? So these kinds of coefficients, like why they exist and why they are. And of course, we'd like to have a theory of gravity. So right now, a whole bunch of people, and I fear they are following the same path as Kepler. We have a whole bunch of people who are nesting spheres inside of spheres, looking for one theory to rule them all. All right. Those people, I'm going to say something that's really rude. I hope I'm not going to get kicked out of here. Are there any string theorists in the house?
I used to do one in
I know. You know I'm talking to you then. That's right. So string theory, for example, that's what they are trying to do. Loop quantum gravity. They're trying to find symmetries that are going to make one gigantic. Frank Wilczek, Nobel laureate in physics, brilliant person. He's written books on this, and if you're interested in it, he's written a whole bunch of books on the beauty of symmetry and how fundamentally we're going to one day find the symmetry that rules them all. I don't think that's going to happen. I think we just live in a random universe, and these values just have these values because we're in some random universe, and there's a multiverse out there, and in most universes there's some other number. Anyway, so some people find that depressing. I find that exhilarating. That somehow I find space for freedom in there, but that's another question. Yes?
Could gravity be described as you form gauge theory, do you think?
So I know that people, for some reason I always thought it was SU10 was the one that I thought I remembered was the one that people had chased the most.
Right, that's right.
Yeah. So I don't know. I mean, SU4 does have a lot of nice subgroups, right? Including SL2C, which is the Galilean. But All right, so I'm going to shift gears in a second and start talking about something more practical. Yep.
So maybe you can give an intuition to the student of what is you.
No. Yes, so that's what I'm going to do now. I really am going to do that now. So this was more just still an introduction. I will do that now. I'll make one last philosophical point. So I'm giving you the physicist's perspective. There is another perspective on this. Jean Dieudonné was a famous French mathematician, and at some debate about math education, he literally stood up during the conference and yelled, "Down with Euclid, death to triangles." He thought geometry, and in particular symmetry, was so beautiful that you had to try to study math without ever visualizing it, so you would never be fooled by the beauty. And so he was part of a team that called themselves Bourbaki, who write this huge series of math textbooks with no pictures, for the precise reason they don't want our analytic minds to be tricked by beauty and geometry. Or Brouwer, another famous early 20th century physician, the construction itself, speaking about math, is an art. Its application to the world an evil parasite. So, engineering physics students, evil parasites. All right, just thought I'd give you that perspective. The world is out there, right? There are people who think math is more like poetry, right? And they think that physics and engineering physics are more like writing advertising copy to sell widgets to Coke machines, right? So, okay. So, I want to try to answer Miguel Angel's question about what those symmetries mean and what I'm talking about. And so for the rest of the talk, I'm going to go pretty specific and talk about a specific kind of material called graphene. So graphene this is an idealized picture of it. Idealized in that each of these gray dots represents a carbon atom. And then these carbon atoms align into a sheet of hexagons, right? This is the idealized picture. We draw these little carbon bonds here as though they're really little stick figures. Of course, really, these are carbon nuclei. And there's all of these electrons around it, 6 electrons for each one, and really this is a whole sea of things. This is actually a picture with an a tunneling electron microscope of graphene. And it got, Guy, and I forgot who the other one, won a Nobel Prize for graphene, basically for this. They took a block of graphite, right? Graphite, which is just some big black rock. They took transparent tape or Scotch tape. They stuck the tape to the big black rock, peeled it back, and then they took another piece of tape and they peeled it back and it back, and they figured out that that was a way to make nearly perfect sheets of graphene. So the 3D rock is graphite. These sheets are called graphene when they're two-dimensional. So this material is one of the most studied materials on Earth right now. For example, there's a famous thing where if you have 2 sheets of it and you twist them at 101 degrees from each other, they have magical conductivity properties, right? And they have amazing optical properties, and they're incredibly strong. It's this material that, whether you're talking about mechanical, electrical, magnetic, or optical properties, they are remarkable. And there are literally tens of thousands of physicists and engineers worldwide studying it, trying to figure out, can we mix it in paint? Can we make touch screens out of it? Can we make new filters for electric batteries out of it, right? Can we do all of these things? So if you want to study graphene, what are you going to do? Well, I'm a quantum mechanic. Right? So one thing I can do is I could write Schrodinger's equation for it. Now, if you haven't seen Schrodinger's equation for it, I can just tell you a few things right here. So this NN, that's the number of nuclei. So you got a sheet, maybe you're not going to do a huge one, but maybe you've got 1,000 nuclei you're going to try to model here, right? And each of those nuclei has 6 electrons. So Ne is the number of electrons, so we've got 6,000 electrons here. This is the kinetic energy. So this is a Laplacian, this is the Del operator, this is a differential 3-dimensional operator squared. for the nuclear coordinates, for the electron coordinates. So again, this is a partial differential equation, 7,000 variables, and it would be a really small sheet of graphene, right? It would be a really small sheet. This is the attraction between the nuclei and the electrons, the repulsion of the nuclei, the repulsion of the electrons. So this says, if I knew the wave function, then this giant differential operator times this wave function would be a number times this wave function. This is called the Schrödinger equation. It's an eigenvalue equation for a differential operator. Even with the advances in technology we have now, not going to do it. Not going to do this. Right? So if we want to make any progress, we have to make, well, we can make approximations. That's certainly true. For example, what we'll often do is we'll say, okay, let's first assume all the nuclei are fixed in the hexagonal pattern, right? That they're actually fixed. Let's also assume, whatever, 5 out of the 6 electrons are actually bound to those nuclei. So we only have to worry about 1 electron per atom. And then, heck, let's pretend the electrons aren't interacting. This is an approximation that was developed in the 20th century, and it turns out it works really well. There's violations, right? And those violations, those places where the approximation breaks down, that's where you build your career, is by finding the special cases, the measurement to detect where your approximation breaks down. But the point is even when you do that, it's still really hard. So the next trick, of course, is symmetry. And so what I'm going to claim, right, is that now what I'm going to spend a little bit of the rest of the time teaching you is to get a feel for how you would even describe the symmetry of this thing, right? So there's definitely, we can see already there's going to be some sort of rotations. There's going to be, like this part is sort of 3 symmetric, and this part is 6 symmetric, and there's reflections, and yeah, so we want to try to describe all this, right? So we want to turn this symmetry into algebra. All right? It's exciting. I don't know what's going to. So we want to turn. That's what group theory is, right? We have these notions of symmetries, and we want to turn them into algebra. Maybe the algebra of matrices. Maybe the algebra of a more abstract notion. Like, for example, let's talk about a triangle. So a triangle is similar to itself if you reflect across any vertex. So there are 3 reflection symmetries here. It is also similar to itself if you rotate it by 120 degrees in each of those directions. So in some sense, if we count then one more operation, do nothing, that's called the identity, we can make a little chart here. Because it turns out if you do 2 of those operations, that's equivalent to doing one of the other ones. So for example, if you flip across A, and then you flip across B, that should be the same as the rotation by D, right? So there's a bunch. So this is an example of a group with 6 elements. This is a realization of that group as the symmetries of a triangle. This is an abstract structure, right? And this abstract structure has properties like, well, I don't need to do these, but right, every element has at least one element that if you multiply it by A times A gives you E, B times B gives you E, D times F gives you E. Every element has an inverse. It has associativity, it has some other properties too. But the point is we can turn this symmetry into an abstract group. And then it's really funny, right? Different kinds of systems can have the same symmetry. Or can have different symmetries, but be represented by the same group. So for example, I've just done the triangle and the plane. If you think of the permutations of 3 objects, all the way you can permute 3 objects. There's 6 permutations. And the structure of how those permutations permute each other is exactly the same as the symmetries of a triangle. Or here is a painted 3-dimensional figure, a prism, which has no reflection symmetries, right? Because that would reflect blue on the white. But it does have additional rotational symmetries through these faces. And the symmetries of this object are different than the symmetries of this object, but they are realized, but they have the same abstract group underneath of them, the same structure at its base. And then here's a weird one. The roots of the cubic equation. Wait, the roots of the cubic equation. Okay, so let me maybe say a few things about that. So, the quadratic equation. How many of you have used the quadratic equation, the solution of the quadratic equation? Why is this so cool, right? It's because no matter what A, B, or C are, they can be real numbers, they can be integers, they can be complex numbers, this formula gives you the 2 roots of this polynomial equation. Sure, because you have this square root in here, like you have to introduce a new mathematical operation called the square root, and if this is negative, if this is negative, you might even have to introduce complex numbers. But this one formula solves all of these equations. Super useful. We know there's applications all over, natural science, engineering, mathematics itself. Okay? How many of you have done the cubic equation? Okay, yeah, I did once in grad school, right? So, right, this equation, guaranteed by the fundamental theorem of algebra, has to have 3 roots, right? And it's written, right, in terms of these different formulas. One crazy thing about these formulas, if you'll notice, so again, this is discovered maybe 16th century, right? I forget all the names in the history, it's a little tortuous. These formulas have an I in them. That really freaked out people in the 15th and 16th century, right? Because they had to be like, what? It was already hard enough. They just invented negative numbers and 0, right? And now they're like, we got I. So I mean, it was a big breakthrough to even have to be able to write these things and acknowledge, oh, we have to take the square root of -1 to make this make sense. But again, I have 4 numbers up there. No matter what they are, I can write an algebraic equation that summarizes basically the properties. For example, if I move A a little bit, I know exactly how these roots move, right? I can do a little bit of analysis. I can see how the roots flow as I change the variables. Okay, so we had a few for cubic. Has anybody used the quartic? Okay, right. So first up, don't use the quartic. I never use the cubic anymore either. That's why we have computers now. Like, it's almost, unless you're literally trying to do something absolutely analytic, you're gonna, any application, you're gonna use a computer and some method to solve for the roots, right? Okay, who's used the quintic equation? No one. If you said yes, you're a liar. Because, right, so people found the solution to the cubic equation in like the 16th century. And then in the late 16th century, early 17th century, from then on, people eventually they found the quartic equation. And they got tanked, right? Like as soon as you found a solution, you got a job, right? This was a whole game people were playing in the Enlightenment, right? And then all of a sudden, so people are like, I'm going to find the quintic equation solution, and I'm going to become a full professor at University of Padua, right? It's going to be awesome. People spent 200 years on this, until finally, literally a French teenager named Galois, and then also a Swedish mathematician ended up starving himself to death on straw. Anyway, long story. The point is, figured out there is no algebraic solution to this equation. If you know a particular value of A, B, C, and D, for certain cases there might be algebraic solutions. And for any values of A, B, C, D, and E, there's going to be a numerical solution possible, but there's no algebraic solution. It just literally doesn't exist. And group theory was invented to prove this. Because, right, this equation should have 5 roots. And these roots, it shouldn't matter whether I do, like, what order I write the roots in. So these roots should have permutation symmetry of 5 objects, S5. That's called the symmetric group of 5 objects. And it turns out when you multiply out the group, when you write out the group table for S5, that's 120 elements, its structure is too complicated. It has ambiguity in it, in a way, and different ways to factor it that mean you cannot solve it with algebra. Right? And that's what Galois and Abel and Ruffini proved, was to literally say there's not enough symmetry of a quintic equation to solve it. For the amount of things you're trying to figure out and the amount of symmetry it has, there's not a mismatch, and so algebra breaks down. So this is a beautiful thing. Again, this is a no-go theorem that tells us this. One of the things that I always like to say is, one of the things this means is, if you're working on a problem and you get a quintic equation or higher, one of the crazy things is then, is you don't know when you move one of these variables just a little bit, you're not guaranteed to know where the root's going to go. It could be totally crazy. And in fact, maybe you've seen pictures of like fractal-like sets for basins of attractions for the quintic equation and the sextic equation, right? Like things get really crazy as soon as you get up to 5. I like to say 5 is different. There's a famous phrase in physics called more is different. And so I like to say 5 is more. Right? So anyway, okay. So that was just a point, right? We want to solve graphene, so we've got to turn, we want to turn as much of the problem into algebra. We do not want to do integrals. We do not want to solve partial differential equations. We want to turn it into algebra and then use algebraic equations, maybe matrices and linear algebra. That would be okay, right? We want to turn as much of it as we can into linear algebra. So to do that, what we really need to do is to understand the symmetries in a plane. And here's just a crazy fact. There are exactly 17 ways to make a crystal in a plane. Exactly 17. Just the same way, there's 5 ways to make a platonic solid. There are 17 ways to make a crystal in a plane. They're sometimes called the wallpaper group or the wallpaper symmetries. Because you can also think about it as there's only 17 ways to say start with a tile and to then tile the same plane to infinity always, right? So there's, for the record, there's 230 crystals in 3D. There's like 4,040. We don't know how many there are in 5D yet. That's still an open question. But anyway, so there's a lot of these fun problems here. But in 2D, we've known this, I think, since the early 20th century. So I want to say a few pictures of these. Now again, this doesn't mean there's only 17 kinds of wallpaper, right? You can have different wallpapers that have the same symmetry. But there's only 17 symmetry groups. So to understand this, a few things about symmetry again. First thing we have to understand are point symmetries. So for example, these 8 objects all have different point symmetries. Different symmetries where you can map them onto themselves but keep one point the same. Think about them for a second, try to classify them. Like, they fall naturally into 2 groups. Can you guess what the 2 groups are? Some of them have reflections and some of them don't. If you categorize them, you find the top set all have at least 1 reflection and the bottom have none. So we call this one, for example, this has 1 mirror plane. In what's called Conway notation, we call that star 1. This rectangle is star 2, right? It's got 2 mirror planes, or mirror lines. We're in 2D. 3, 4, we can keep going forever. This has no symmetry at all. I'm just going to call that 1. That has a 2-fold rotation symmetry. So again, in Conway notation, you don't put a star, you just say a 2, right? I can rotate this by pi or 180 degrees and it maps onto itself. Right? That thing, which looks like the symbol of Sicily, if you've ever seen it with the legs. Right? That's the 3. This is the most neutral 4-fold symmetry I can come up with from here. Some of you, all right, already, you know what I'm talking about. Yeah, so anyway, so again, this thing, right, you can only rotate it, you can't reflect it. There will be another version of this, right? For all of these, maybe these are all the right-handed versions. There's also a left-handed version that if you try to use a reflection, you map onto it. Yeah, so again, these are called kaleidoscope symmetries and gyration symmetries. So kaleidoscope if you have mirror planes, gyrations if you don't. Right? That's the flag of Hong Kong. Hong Kong, yeah. It's a pretty flag. Right? I took me the blue thing is mine, yeah. That's the devil's side. All right. Anyway, I'm not going to do this right now, but this is a fun little activity, right? Like whenever I see a font set, like I like fonts, right? I always think to myself, okay, what are the symmetries of this font set, right? So you can look at these things, right? Different fonts have different symmetries, and this very standard font, right? Like A has one vertical symmetry, C one horizontal, X has two reflections, N no reflections but one twist, right? And again, you can sort, or then there's R is nothing, R. So you can sort them all out, right, the groups. Oops, yeah. I put B here, sort of floating between 1 and star 1H, because, right, this B looks a little smaller on the top than the bottom, but you could imagine a font where it's totally symmetric, right? I like those kinds of block fonts that are totally symmetric, but that's because I'm a mathematical physicist. And you know, it's like a disability in some sense. All right. Okay. So actually, the way these symmetries then are labeled is each of these symbols. So again, this is called Conway notation. I don't know if you know who John Conway was, mathematician. He's the person who ended up sort of leading a project that classified all what are called the finite groups. Right? There's this beautiful book where he classified all the finite groups. I mean, working with a team, he discovered some really big, simple finite groups, like really huge groups with millions and billions of elements. He also invented something called the game of life. Have any of you ever seen that computer program, right, with the little rules? Yeah. Yeah, so he invented that like as a doodle, and then it turned out that doodle game is actually computationally equivalent to a Turing machine. Like anyway, so he's got a lot of good stuff going on. The point is, he came up with this notation. So let's look at this a little bit to understand them. So these numbers then tell you, like, so this means there are two different fourfold gyrations and one twofold gyration. This means there's a fourfold reflection, and a twofold reflection. This means a fourfold kaleidoscope or reflection, and sorry, I said it the other way. Fourfold gyration and a twofold reflection or gyroscope. So yeah, so a kaleidoscope. Sorry. Yeah. Let me see if I can do this fast. Okay. So we've already talked about reflections and the rosette symmetries. We also need translation symmetries. So, for example, this wallpaper has two translation symmetries. I can move the flower up, or I can move the flower over. Right? I got two translation symmetries, and they are linearly independent. Right? I can't. Every other translation I can build at a basis of these, an integer multiples of these, but these are my bases. Notice this particular part, there's no other symmetries in this, right? But I could make like a parallelogram tile that contains one flower, and then again, I can tile the entire plane with just that one tile, right? Just by translating that one tile all over. If I look here, right, well now this particular figure, again, you have to notice that these really are spirals that have a left-handedness to them, right? So you have to take into account, otherwise you might miss a little bit of the symmetry. Yeah, you can do the same kind of thing there. Make a little tile, and pattern it all over. Where you choose to make your tile is arbitrary, but once you do that, you have the whole thing. So those are called translations. You need one more kind of symmetry called a glide reflection. Here I've done a quasi one-dimensional version of it. A glide reflection is where you translate and then reflect. So right, a translation, this is a symmetry, right? But if I just go halfway, then it's not a symmetry. I have to go halfway and then a reflection. And that's called a glide symmetry. A glide symmetry. So it turns out the symmetries of all the wallpaper groups can be broken into these 4 kinds: reflections, gyrations, kaleidoscopes, translations, and glide reflections. So let's show you one, for example. This one's called 3 star 3. So again, there's got to be a 3-fold axis that does not have reflection symmetry and a 3-fold axis that does. So let's see how this works. Well, so first off, this is not the only pattern that has 3 star 3. All of these patterns have 3 star 3, right? Maybe this is the easiest one to see, like, oh, around this point, I've got a 6-fold, a star 3, and around this point, I've got a 3. Maybe you can see it here. So, for example, all of these blue triangles don't have reflections, right? Notice for the blue triangle, if I go out one of the green leaves, I make a right turn to a petal. Green. So the blue triangles do not have reflection symmetry. But the red triangles at the center of the flowers, they do. Right? They do. And so we have, through all of those, we have reflections. Yeah, so we have all these different reflection planes. And so this is what the reflection planes look like. Yeah. Just trying to make sure. How are we doing on time? Good. Okay. I'm almost done. So the point is, yeah. So the 3 we just have. So this pattern then, right, can be mapped onto all of these other patterns. Okay. Well, so for example, all of these shapes, their fundamental tile is a hexagonal rhombus, but they have all these different symmetries. This one, star 632, which means there's a 6-fold axis with reflections. There is a 3-fold axis with reflections and a 2-fold axis with reflections. This is the most possible symmetry you can have in the plane. This is literally the most possible point symmetry and overall the most symmetry you can have at all. And there's no more you can do. You can't have a tiling of a plane that has more than 6-fold symmetry. That is another thing you can prove from Euclidean geometry. So this list is complete, and graphene has the absolute most possible symmetry of any material, and that is why we are led to it for all of its properties. This means that when I do the algebra, first off, I can do the algebra better than most materials, and there really are properties of this that can be determined from the algebra. The algebra even gives topological structure to the material. This is the most interesting material in 2D. All right, well, so I slipped a little bit there, right? Because I did sort of slip into sort of making some sort of ontological claim based on beauty, right? That's what I did. I made a claim about reality based on beauty. Just want to sort of point that out, because there's a really famous case where there's a trick where if you have a crystal, you shine X-rays on it, and the X-rays bounce back, right? And the pattern that the X-rays bounce back are how you can determine the shape of the crystal. One of the most famous examples of this was Rosalind Franklin, who used this technique to figure out the DNA was a double helix, right? And you can sort of see, like, oh, these kinds of dots mean this kind of pattern and all this. So if you have a hexagonal lattice and you shine X-rays on it, you get a 6-fold reflection pattern. Well, so this guy Daniel Schexman, he started publishing stuff like this. And people are like, Daniel, you are an effing idiot. Because this has 10-fold symmetry. 10-fold symmetry is not possible for a crystal, for one of these infinitely repeating crystals. And people literally are like, Dan, I don't know what you're doing, but you are wrong. Your machine is calibrated wrong, or you're interpreting something wrong, or you're somehow laying images on top of each other. You're doing something wrong. And he had to fight to years until people finally realized, like, okay, we can actually do, scanning tunneling electron microscope of the crystals he's talking about. And it's like, oh, we get a pattern. So now this is another TEM, And I don't know if you can sort of see this. It's not super clear in here, but it looks like there's a bunch of sort of tenfold patterns, and they sort of repeat, but then they sort of shift, and they don't quite repeat, right? Like, it sort of looks like a crystal, but it's a little crazy. Maybe we'd call it a crazy crystal, or maybe a quasi-crystal. Quasi, if you sort of switch the... Well, and it turned out these things had actually been discovered. Roger Penrose, who actually won a Nobel Prize for his work in relativity, had figured out that you could make something called a quasi-crystal, an aperiodic tiling. You could take some polygons, and you could tile the plane in a way where they almost repeated, like a crystal, but in fact, they never actually do. They never quite repeat. As you keep going on, like, you keep thinking like, okay, I go over here, I go, no, that's a little different of those, right? You see, yeah, so this subject of aperiodic tiles and quasi-crystals, there was actually just a major breakthrough last year, where somebody figured out just last year that there's actually a way to make this with one tile. Penrose was famous because this is one of the simplest ones. This is called is it the kite and dart one? But there's actually a way, they call it Einstein for German for one stone, not for Einstein, whatever. The point is this is a whole subject, and the way we now think about these things is if you have a quasi-periodic tiling, it's because maybe you've got a 4-dimensional or a 5-dimensional lattice, and you're just taking a 2 or a 3-dimensional slice of it. And because when you take a slice, that angle can be irrational, it's not going to line up again. So there is an order in these things, but this is a crystal in 5 dimensions. And that's why we're seeing sort of a shadow of a 5-dimensional crystal here in this quasi-crystal, and we actually can get tenfold symmetry. And so finally, of course, he convinced people, right, that this was a real material found in nature. It turned out it was from a meteorite, if you can believe it, right? So literally, quasi-crystals are from meteorites that fell from space. Those are the first ones discovered. It's just bonkers, right? He gets a Nobel Prize. Suddenly, this abstract math becomes a hot topic in understanding how matter works, right? How crystals are formed under extreme conditions. So anyway, so symmetry can be a powerful tool. It can be a beautiful guide, but it can also be a trickster, right? It nearly tricked people into firing Dan Sheckman. All right, so those are my conclusions. Symmetry is useful. It identifies and classifies possible realities, and it turns analysis into algebra. Symmetry is beautiful. Crystals of order, conservation, and unification, but it's so beautiful that it can turn a physicist into a mathematician. But they won't know it, right? They'll still think they're doing physics. If you're interested in this idea, there's a beautiful book by Sabine Hasselfelder where she argues what's wrong with particle physics is that too many physicists have been tricked by symmetry, and that we need to reorient particle physics in particular, so that we now think about what can we measure and let that guide us instead of what beautiful symmetry might be out there. Anyway, so this is sort of like, it's like I'm an alcoholic. I'm a reformed particle physicist, right? I'm a reformed particle physicist, and as a result, I'm very, anyway. All right, thanks for your attention. That's that.
You can make it in Spanish and English. If you don't feel comfortable with English, what you can make in English. You can make it in Spanish.
Just one brief comment. Of course, symmetry is a very powerful tool. Symmetry breakdown itself is even more powerful.
I agree entirely. And that's most of my research. That's what I do is, and that's even right. Yeah, absolutely. You're right. Yeah. And even more generic in some sense. Yeah.
It's called spontaneous symmetry breaking.
Well, yes, spontaneously or otherwise.
Yeah, that's right. Quick comment. He mentioned in one moment the magic angle into the graph. In Spain, there are 2 candidates for the Nobel Prize that can demonstrate some time. This is Ignacio Sirac from quantum computing and trust. The other is Pablo Jarillo from Valencia, about my age. Who's in MIT, and I think now he's in Barcelona in sabbatical, and he experimentally realized this mathematical angle. He did not do the theory.
No, Alan McDonald did the theory. Who I happened to, he was at University of Texas, and I took my last class for my PhD with him. And I was a particle physicist, And this guy was such a good teacher. If I had to do it all over again, it might have been condensed matter, right? But it was my last semester of PhD, and I had to get out of there.
I have one comment. So first of all, I think that thank you for the lecture because it was very beautiful. And if I'm not wrong, I think that these tile symmetries in the plane can be found, all of them can be found in the Alhambra tiles. So this is, as far as I know.
I believe that's true. I can't wait to visit. I believe that. I actually think it's 16 out of 17. I think there's one missing, but I think it's almost all.
Maybe, yeah, for sure.
We had a talk like a month ago or so, and they told us that they are like studying those type of symmetries in quasi-crystals with D-wave computers, like from the is that like a new interesting field, or?
Well, it's funny you say that, because I literally just read an article yesterday where someone has figured out. So yes, there is actually a field here because there's a connection between these and quantum computation. So one of the things that is interesting about quasi-periodic tiling is that, and I'm not an expert in this, and I want to make sure I say it right, so but I might say it wrong. But so you have strong local correlations about, you can sort of predict what tiles are near you, but you have zero information long range, right? If I just look at these two, I can't detect the correlation. And so someone realized that you could use this to make quantum error correcting codes. Because even though you can't see this correlation like here, if you put this tile wrong, it won't lay right there. And so you could somehow use these hidden long-range correlations that are not obvious to make to build robust qubits and make quantum error correcting codes. And so literally that's a new paper that just came out in the last few months. So I do think, and Penrose himself has done a lot of work on the relationship between quasi-periodic tiling and computability. And then of course quantum computers are trying to figure out what is classically computable, what is quantum computable, and so this is an active area of research. It's not my specialty, but it is active. Yeah.
Another comment on D-wave is that D-wave have different generations of D-wave have topology. So they cannot be connected all to all. So qubits are connected in some topology in some way, and it's quite complicated how they are connected, and chimera and this one and this one. So what they are restricted, because you codify your program in the connections and the topology.
Is that what they're doing? They're literally making the connection with quasi-crystal?
I
get it. That's a good idea.
I don't know.
Like, they are not computing something, they're just
They're
using
literally.
the chip to.
I see. Okay.
To realize probably.
Cool. Cool. All right.
This is my guess.
Just a comment, perhaps a question also. In fact, thank you very much for the talk, very nice. You have talked about infinite systems with periodicities or symmetries, whatever. But in nature we go from disordered structures to completely ordered or symmetric structures, and we have a plethora of material passing through this way, and there's a lot of things. And from my knowledge, there is a way to classify, that you can try to classify all of that materials, is the hyper-uniformity. I don't know if you have talked about that. And it relates the number of degrees of freedoms that are constrained with respect to the free that you have in the system. And in fact, if you look only 1D systems, you can move this hyperuniformity using a parameter going from 0 to 1. And if it's 0, everything becomes disordered.
Okay.
Disordered.
Disordered. Okay.
When you arrive to 0.5, in fact, from 0 to 0.5 is something you have some spatial correlation,
Yeah.
and from 0.5 to 1, the only possible solutions to your systems are purely symmetric and purely periodic structures.
Okay.
So I find there is, I know this connection with hyperuniformity,
Okay.
and I think it's a beautiful aspect also to mention.
Yeah, I know there are several approaches to sort of going from, say, point symmetries, local symmetries, uniformity, right? I mean, I know that, so hyperuniformity, look that up.
Just have a look, it's
Yeah.
very nice.
Yeah, nice.
And just a question, because I'm always interested on that, I never thought on that. So imagine that you have an infinite system, disordered, and you find out that in some places you have some local symmetries. What kind of implications you can have to...
So I know some results for quantum systems, right? When you have these local symmetries, you literally can have a few quantum states that are special, right? Yeah, and if you have enough of them, you can make what are called flat bands. There's a colleague of ours, Peter Schmelker, has done a nice classification of some of those, and he's actually then worked with optics people who can make some really pretty experiments where you have a disordered system with just a few little points of local symmetry, a really local, like say, even just like a few little pairs that are lined up nicely. And and you really can see those effects. You can get sort of a coherent raising between these different sections, or coherent gradients, I should say, between these different sections.
Other connected thing is that when you have chaos, classical quantum chaos, the concept of chaos is that you have broken all symmetries. So when you have some conserved quantity, you have regularities. You can imagine that something repeats in the dynamics. When you break everything, you have random matrices, random elements, so on. But you can have what is called scarves. So you can have some regions in which you have some regularities. And if you restrict your dynamics to this part, it looks like conservative.
Yeah.
You can conserve and everything is
You
nice.
make coherent quantum systems.
So when you have some regularities in part and you stick to energies around it, you can have something that resembles conservative dynamics.
And I just want to say one last thing, and maybe I'll close it up. So again, I study few body systems. So like I'm studying, say, 3 atoms in 1 dimension, or 4 atoms in 2 dimensions. Well, if you've got 4 atoms in 2 dimensions, that's sort of like you have 1 particle in 8 dimensions, right? So when I talk, every once in a while I kept mentioning these higher dimensional things. That's not just academic, right? Like I'm literally thinking about 3 particles in 2 dimensions. Well, that's 6 dimensions. So I've got to think about symmetries in 6 dimensions. And so that's actually where, so that's the fun game that I get to play right now as a mathematical physicist, is trying to find these symmetries in these dimensions. And think about crystals in 6 dimensions. Yeah, so, okay. He was only thinking about it.
I'll do one more comment. So here, the list is not comprehensive. So if you have people working in photonic crystals, on photonics and optics, where they do a lot of symmetries and the classical solutions. You have people working like in acoustics, where you also use symmetries, right?
Yeah.
Photonic crystal symmetries and all that, and it's a very strong tool also. You have people working in 2 connected fields to this, which are just in the moment of jumping to them, which is in fractals, dynamics in these systems, nonlinear dynamics, chaos, and all that. So the Institute of in Japan or Institute of Mathematical Physics, there are more experts on all that. Right? And there's many groups working in different branches, which are in quantum physics for sure, work with this, and so on and so forth. So there's applications here in UPD of people using all these different fields. The ones that are photonics, optics, maths.
Well, thank you for your attention.